Good morning, and thank you everyone who is joining me today. My name is Rocco Pietrini, and I'm going to talk about my dissertation work, which is entitled Deep Understanding of Shopper Behaviors and Interactions in Intelligent Retail Environment. My advisor is Professor Emanuele Frontoni. The main goal was to develop computer vision applications to understand human behavior in a retail context with specific tasks such as people counting, shopper analytics, and re-identification, improving the accuracy of the existing solutions. The research presented in this thesis has been conducted in the VRAI Vision Robotics and Artificial Intelligence Research Group, in cooperation and collaboration with the company Grottini Lab, which makes the retail intelligence and the shopper behavior understanding its core business. I want also to add that part of this research has been conducted during my visiting period at the University of Central Florida. The main contributions of this thesis are the research and development of the new VRAI framework to solve three challenging tasks in human behavior analysis in retail context, which are people counting, shopper analytics, and re-identification. Then the deployment and validation of real applications derived from large experience with over 16 million of shoppers observed in 3 years in different countries and in different type of stores, and the collection and release of 3 new datasets collected in real stores and manually annotated. This presentation is divided in sections, and for each section we will see how the different tasks that are listed in this slide are treated. First of all, the scientific state of the art of the people counting problem, which means to count how many people are in the camera area. And many of the approaches in the literature present a frontal or a side view, but this is prone to common problems like occlusion or counting in crowded environments. The same can be said for the re-identification problem. We have many datasets in the state of the art, like the Viper dataset or the Caviar 4AD dataset. Both of them, like many others, uses a frontal or a side view, but again, this is prone to occlusion and complex background modeling. So we will see how in my thesis we can overcome these problems. Then we have the shopper analytics, which means to understand what people do when they are in front of the shelf. We have 2 main approaches in the state of the art. One is by Liciotti, and is called shopper analytics. It uses RGBD streams with the classical feature-based approach. And then we have the new approach by Singh, presented at CVPR 2017, which uses only the RGB stream, and they also released the only existing data set for action detection in a retail environment, which is MERL. But we will see that there are many limitations with this approach because they don't do any object matching, and also it is not a real-world data set because it's collected in a lab. Understanding shopper behavior is really challenging. The interest in the topic is also rising in the industry. There are many startups and companies active in this field recently. The most notable one is Amazon, which launched 2 years ago Amazon Go. That is the first fully automated cashierless store. However, we can look at this picture where the ceiling and the shelf of an Amazon Go store are depicted. If we consider that an Amazon Go store is only 100 square meters on average, so it's really small store, but it has thousands of different sensors to understand the human behavior. This is because while the retail environment has several favorable characteristics for computer vision, such as reasonable lighting, the large number and diversity of products sold and the potential ambiguity of shopper movement means that accurately measuring the shopper behavior is still challenging. This is why at the beginning I decided also to face some technological challenges. So from a technological point of view, I wanted solution deployable in existing store. So hence they should be non-intrusive in their installation and scalable and capable of running on the edge. So with an high configurability for a different type of store, the algorithm proposed in this thesis can be run on low-cost hardware directly on the edge. All the solutions are part of the so-called VRAI framework. The first one is the people counting. People counting refers to detect and track how many people are passing under the camera. Using a top view approach allows to minimize occlusions even in a crowded scenario. I define a crowded scenario when there are more than 3 people in a square meter. Usually this kind of problem are tackled using a feature-based approach, but we will see how moving into deep learning can take a big advantage. The first step was to collect a new dataset, the TVHeads dataset, top view heads dataset. It contains 1,800 depth images, 16-bit encoded, together with their 8-bit scaled version in a QVGA resolution, and it has been manually annotated for a semantic segmentation problem, highlighting the head silhouette, and it has been released to the community. Then with this dataset, I developed a new neural network that is called VRAI-Net1, that is basically an evolution of the existing UNet3. And it has the common structure of encoder-decoder. The procedure is composed of 4 layers, and each layer combines 2 types of feature maps. It is basically formed by 2 branches. The first uses an up convolution layer to upsample the activation of the previous layer and the rectified linear union function to avoid the vanishing gradient problem. The second branch joins this with the corresponding layer of the contracting path with the dropout layer to prevent the overfitting problem. Then these 2 branches are merged using an equivalent layer thickness that can squeeze up together the 2 layers. Looking at the results, we can see from the table that the VRAI-Net1 outperforms all the other networks in the state of the art. I compared all the networks using the same dataset and using the metric evaluations commonly used in segmentation problems like the Jacquard and Dice indexes, together with the accuracy, precision, recall, and F1 score. And we can see that even the results are pretty high and close each other, also for the other networks. What is interesting to note is that this network is much simpler than the other, because it has only 2 million parameters, while the UNet3 has 8 million parameters, and the ResNet, for example, has 10 million parameters. So the training and also the prediction are really fast and can be computed directly on the edge. The second problem is the shopper analytics. Shopper analytics means to understand what people do when they are in front of the shelf. We already have some information, for example, how many people are passing under the camera by the previous algorithms, and we can construct what is called the conversion funnel. So I have the total number of people passing by the camera. I can understand how many of them stops in front of the shelf, how many of them interact with the shelf, and how many of them actually buy something, picking up something from the shelf. And we can see that using a top view approach together with the depth stream allow us to exactly match the action with the product. We can see from the product map that every action is exactly linked with the product. We have a green bubble when they picked up something from the shelf. I have a red bubble when I put something back in the shelf, and a yellow bubble when I touch something in the shelf. So the problem was initially defined and tackled with a feature-based approach with 3 classes of interaction: positive, negative, and neutral. But this kind of approach that basically compared the area of the end entering and exiting the shelf area is prone to many problems, like a small product for that the area is comparable with the size of the hand, bad surface for the infrared streams like plastic or glass. And also with this approach, we cannot distinguish between the customers and the staff while they refill the shelf. And also we cannot avoid fake interactions due to unintentionally approaching the shelf with an elbow or a shopping cart. That's why a move into deep learning will solve these problems and will be necessary. So I first collected a new dataset, the Undestanding, which contains almost 14,000 images, RGB and depth, collected over 3 months in 10 different shelves in 4 categories. They have been manually annotated and they have been released to the community. This time we have a classification problem. I also decided to add one more class which denotes the refill operation. I developed a new neural network, the VRAI 2. Well, what is interesting here is the use of the inception module. While in classical neural networks, we choose to stack a different number of filters with some kernel size, here we can use all of them and in parallel, and this the layer that select the most appropriate feature to model the problem. Then at the end, we also have a global average pooling layer that avoid the use of a fully connected layer to map with the 4 classes we have in output. In this way, the network is much simpler. We can see from the result that the accuracy of classification is 93% and is the best one compared to other networks in the state-of-the-art of classification problems. But we also can exclude now all the unintentional interaction. One of them is depicted in the gray picture where the shopper approached the shelf area with his elbow. And also we can detect and avoid all the refill operation made by the staff. Then I decided to approach the problem of the interaction analysis from another point of view, and I took the only existing data set for action detection in a retail environment, which is the MERL. The problem of the MERL dataset is that is it temporarily annotated for action detection, but it only uses the RGB stream, so it cannot match the action with the product. So I decided to build another dataset on top of it. I selected 1,000 frames from 10 different videos, and I semantically annotated the frames to highlight the hand of the customer. So we have again a segmentation problem. Then I used the refinement network, which is a network, a multi-path refinement network that can provide high resolution maps in the output. I used the network pre-trained on ImageNet and trained again on just 1,000 images. So what I did was transfer learning. And we can see from the result that the accuracy is pretty good with the mean intersection over union of 0.7, even using just 1,000 images. Then we have the last step of the VRAI framework, which is the re-identification. Re-identification means to assign to different instances or images of the same person the same ID. So we go from a fully covered area to a sparse camera system. We have cameras located in different categories of the store, and they don't share any overlapping area. I want to re-identify the same customer in different locations of the store. I started collecting a new dataset, the TVPR2, Top View Re-Identification 2, with 1,000 people in more than 200 recording sessions, with depth and color stream in QVGA resolution, and it has been made publicly available for the community. The challenge here is to perform re-identification from a top view point, from a top view configuration, because usually you do it with a frontal view where you can count on things like face detection, and it is much simpler. Then I designed the new neural network, the VRAI 3, which share the same structure of the VRAI 2 with the inception module. Here adapted for an output layer with 1,000 classes. And the results, as we can see from the table, I compared this network with the state-of-the-art methods in both machine learning and deep learning. And the VRAI 3 outperforms all of the others. And also it is interesting to note the cumulative matching curve that is depicted on the left, that is commonly used to evaluate the re-identification problems. It represents the expectations of finding the correct identity in the first n identity. And we can see that the VRAI 3 curves is the best one. And also it is interesting to note that from the graph on the right, that the accuracy doesn't decrease so much when the number of people increase, and that is really good for the identification problem. And what are the uses of identification in retail? For example, the evaluation of the dwell time inside the store by the identification of the same person entering and exiting the store, or the identification of the returning customer at the store level or category level, or the store flow of a single person passing by different categories. So altogether, the algorithms that we just saw forms the VRAI framework, where there are a single RGBD image acquisition with a single sensor. Then there is a pre-processing stage, and then the frames are fed to the three networks. The data coming from the networks are further integrated to have a comprehensive view of the shopper behavior. This is deployed in a real application. The data flow is depicted in this slide. We go from the raw data produced by the sensor that are elaborated by the networks. Then the elaborated data flows into the cloud, where there are Amazon Web Services, different services that aggregate and further process the data, preparing them for the presentation. So the data are available to be presented in a dashboard like this, where we have some KPIs. We can see, for example, the funnel. So we have the total number of people entering the store. We can see how many of them visit a specific category. We have the conversion ratio. So how many of the visitors actually stop by a category or actually buy something. Then we can build more complicated analysis, like the heat maps. We can construct an horizontal heat map where we can see the common path of the customers, or something new that is the vertical heat map, where we can look at the shelf from a frontal view and see what are the most interacted product and how they relate to each other. So this has been validated by a large-scale worldwide test. where over 16 million of people and 2 million of interactions has been monitored in the last 3 years in different countries around the world. Future direction will be to combine the hand detection with the shelf interaction classification and apply this approach to real-world video dataset, and also to move from a frame-based method to action detection method to increase the robustness of the approach and to generally extend the dataset and the algorithms for a better generalization. I want then to list some of the publications that I did during my PhD. And last but not the least, I want to thank every single person that have been part of my PhD, starting from my colleagues at VRAI, then my friends and my colleagues in Grottini Lab, my family. Thank you all.